Hello. In this video, I want to talk about probably one of the most challenging parts of linear programming problems, and that is the setup. Linear programming problems come to you not as a set of equations or inequalities. It comes to us as a word problem, and not just any word problem. Usually the word problems, the information is scattered all over in different sentences. You might take one equation or inequality from three different sentences. And it's sometimes difficult to even know what your variables are. So what I want to focus on right now is how to think about these things and what to look for in the word problem to see what the variables are and figure out what the constraints are and what the objective function is. If you can do that, then you can set up your problem. Now, what I would look to first is look at the question asked. And the question asked is usually going to be the very last thing. So I would skip down with my eye and look at what question is asked. That will tell you, one, what the variables are, and what the objective function is, and finally, whether we are maximizing or minimizing. Next, once we have determined what the variables are, we can then look back at the previous sentences and determine what the constraints are. In many cases, what we can do is we can determine, if we've already determined what x and y are, we can then write x and y for the particular things that they represent in the problem. And we'll go through a few examples and show how this looks. So here's our first example. A calculator company produces a scientific calculator and a graphing calculator. Long-term projections indicate an expected demand of at least 100 scientific and 80 graphing calculators each day. Because of limitations on production capacity, no more than 200 scientific and 170 graphing calculators can be made daily. To satisfy a shipping contract, a total of at least 200 calculators must be shipped each day. If each scientific calculator sold results in a $2 loss, but each graphing calculator produces a $5 profit, how many of each type should be made daily to maximize net profits? Now, I'm not actually going to solve this in this video. The focus here is just the setup. So let's look in the problem and see if we can determine what the problem is telling us. So let's take the first step. Let's look at the question being asked. If each scientific calculator results in a $2 loss, but each graphing calculator produces a $5 profit, how many of each type should be made daily to maximize net profits? Now, right there, that should tell us what our variables are. They are types. They are the numbers of each type of calculator. So we can consider the scientific calculators to be our x values, and the graphing calculators, the number of graphing calculators, can be our y values. And so that also tells us what our objective function is. Our objective function is negative 2x, because scientific calculators give us a $2 loss, and a graphing calculator gives us a $5 profit. So 5 times the number of graphing calculators. That is our objective function, negative 2x plus 5y. And we also know we are trying to maximize our profits. Now what we can do is we can go through the problem and mark with an X every place we see a scientific calculator. So here is a scientific calculator, and here's one here, and that's all I see as scientific calculators. Now graphing calculators are Y's. There's a Y there, and there's a Y there. So we need at least 100 scientific calculators and at least 80 graphing calculators. But we also have no more than 200 scientific calculators and no more than 170 graphing calculators. So in other words, the number of scientific calculators needs to be between 100 at the minimum and 200 at the maximum. And the number of graphing calculators needs to be 80 at a minimum, this is Y in this case, and 170 at a maximum. Now there's one more constraint, a total of at least 200 calculators. At least should make you think greater than or equal to. What is the thing that's going to be greater than or equal to? Well, we are shipping X number of scientific calculators and Y number of graphing calculators, and some combination of those has to be at least 200 to ship each day. These are now going to be the constraints. And these are what we are going to be graphing. As I said, I'm not going to graph them here, but this is what we would graph, and once we graph these, we would find where the feasible region is, and we would find those vertices by solving, and we're going to address that question in another video. Okay, here's another example. Let's get a little practice in on this. You need to buy some filing cabinets. You know that cabinet X costs $10 per unit, requires 6 feet of floor space, and holds 8 cubic feet of files. Cabinet Y costs $20 per unit, requires 8 square feet of floor space, and holds 12 cubic feet of files. You've been given $140 for this purchase, though you don't have to spend that much. The office has room for no more than 72 square feet of cabinets. How many of each model should you buy? So that's our clue right there. How many of each model? How many of cabinet X and cabinet Y should you buy in order to maximize storage volume? So we know we're dealing with a max. Our objective function is going to involve cabinet X and cabinet Y. And we are trying to maximize storage volume. So let's look at volume. Well, volume is cubic feet. Cabinet X takes 8 cubic feet, and cabinet Y takes 12 cubic feet. So if you have X number of cabinet X, then it's going to take 8X cubic feet. If you have Y number of cabinet Y, it's going to take 12Y of cubic feet. And that is what we are trying to maximize. Now, we now have the constraints. Okay, now conveniently, cabinet X, all of cabinet X's stuff is in one sentence, and all of cabinet Y's stuff is in one sentence. What we need here is there's several different things about cabinet X in one sentence. First of all, and we can even write this down, square footage. Okay, cabinet X, well, I guess that's not the first thing, but we can make it first. Cabinet X is 6 square feet, and so 6 times X is going to be the number of square footage occupied by cabinet X. Cabinet Y has a square footage of 8 each, and so there's going to be 8Y. Now, the office has room for no more than 72 square feet of cabinets, which means less than or equal to 72. Now let's look at cost. Cabinet X costs $10, so X of them will cost 10X dollars. Cabinet Y costs $20, so Y of them will cost 20Y. And we have a constraint on money. We have been given $140. We can spend that much or less. And so those are our constraints. And of course, I didn't mention this in the previous example, but I think it's understood that x and y both have to be 0 or greater. We're not going to have negatives. So whatever our graph is going to be, it's going to be in the first quadrant, and it's going to be in this area right here. And so that's going to form some more boundaries to our feasible region. Let's move on to another example. A store sells two types of toys, A and B. The store owner pays $8 and $14 for each 1 unit of toy A and B, respectively. 1 unit of toy A yields a profit of $2, while a unit of toys B yields a profit of $3. The store owner estimates that no more than 2,000 stores will be sold every month, and he does not plan to invest more than $20,000 in inventory of these toys. How many units of each type of toy should be stocked in order to maximize his monthly profit? So we have maximum profit is what we are aiming at here. That is our objective, and so that is our objective function. Well, where did we see profit before? We saw profit in this sentence right here. A lot of times they will put that right before the question, but they didn't this time. So here we have the information kind of hiding in that word problem. Toy A, let's consider x to be number of toy A and y equal to the number of toy B. So the objective function will be toy A yields a profit of $2, so 2x will be the total profit of toy A, and toy B yields a profit of $3, and so that's going to be 3y there. So that tells us we're maximizing, it tells us what our variables are, and it tells us what our objective function is. Now what we can do is look at toy A. The store owner pays $8 for toy A, which is x, and $14 for toy B. So, how much it costs? How much they cost? Well, toy A cost $8, so 8 times x is going to be how much total paid for toy A, and 14y is how much is paid for toy B. What is our constraint on cost? Well, where else do we see money? Does not plan to invest more than $20,000. So no more than or less than or equal to $20,000. Okay, so that's cost. Next, we're going to look at sales. Sales is the other constraint. The store owner estimates that no more than 2,000 total toys will be sold every month. So in other words, the number of toy X plus the number of toy Y, rather X, which is the number of toy A, and Y, which is the number of toy B, will not exceed 2,000. And as far as I can tell, that represents all of the information in the problem, and so that is where we then go to work graphing and doing all the rest. We're going to do one more example and to get a good feel for how these work. A company produces two types of tables, T1 and T2. It takes 2 hours to produce the parts of 1 unit of T1, 1 hour to assemble, and 2 hours to polish. It takes 4 hours to produce the parts of 1 unit of T2, 2.5 hours to assemble, and 1.5 hours to polish. Per month, 7,000 hours are available for producing the parts, 4,000 hours for assembling the parts, and 5,500 hours for polishing the tables. The profit per unit of T1 is $90 and per unit of T2 is $110. How many of each type of table should be produced in order to maximize the total monthly profit? So we are maximizing profit. This seems to be a very common thing in linear programming. It's also a very common thing in calculus optimizations. So we're maximizing profit. And profit does happen to be very near the last sentence. So let's consider x to be the number of T1 tables and y equals the number of T2 tables. It helps to write these things down because you will then be able to reference things a lot better. So the profit per unit of T1 is $90, and there are X of them. The profit per unit of T2 is 110, and there are Y of them. So that is the function that we are going to be maximizing. This also gives us our variables. So wherever we see T1, we put an X. Wherever we see T2, we put a Y. So if we look at this, I'm going to use a different color pen here. If we look at the question, there are three different parts to this. There's production, there is assembly, and there is polishing. That's going to give us three constraints. So production, for T1 it takes 2 hours to produce it. For T2 it takes, 4 hours. How much is allotted to production? No more than 7,000 hours. Next is assembly. So for assembly, 1 hour is available for, it takes 1 hour to assemble T1, and it takes 2.5 hours to assemble T2. And for assembly, we have available 4,000 hours. Lastly, we have polishing. And to polish T1, we have 2 hours. It takes 2 hours to do that. To polish table 2, or T2, it takes 1.5 hours. And the amount of time available for polishing tables is 5,500 hours. And this covers all of the information that is in this problem. Now, you may notice that we are drawing that each element of the inequality is drawn from a different question. This part, or from a different sentence rather. This part was drawn from the second sentence in the question. This was drawn from the next sentence. This was drawn from still another sentence. That is going to be a very common thing. This is the way information often comes to us. It does not often come to us in the nice, neat, organized ways that we would like. So you need to be very careful and pay very close attention to what your variables are and where they show up in the problem, and be able to match things properly. It takes practice, but you can get better at that. In my next video, we're going to be looking at a linear programming problem. We're going to be looking at other elements of a linear programming problem, the graphing, the feasible region, and the finding the vertices and then maximizing.